Let's start with elementary concepts of electrical engineering. We have certain basic elements in electrical engineering. They are actually idealized models that can be represented and that can be mathematically analyzed. What I mean to say is, we may have a long wire. Try to understand this. The resistance of this wire is, given by R rho L by A. A is the cross section of this wire, L is the length, rho is the resistivity. So this is L from here to here. If this wire we see cross sectional view, this is your, if this is radius is R, your area is pi r square, and rho is the resistivity of this material, the material with which this has been made. So this is a wire. What we do, we idealize it. We say, or we represent it like this. This is R. So this is what, when I said idealized models. So we have three basic elements that are idealized models of existing materials, existing devices. They are R, L and C, that is resistance, inductance and capacitance. So first of all, let's see resistance. It is a dissipative device. Dissipative in the sense, it dissipates energy. If you provide energy to it, it will dissipate energy. When current flows through a resistor, let's say this is our resistor. If current flows through this resistor, this is I. If you flow this current, this resistor will dissipate energy in the form of heat energy. Okay, and the process is irreversible. If current goes through it, this will start dissipating energy in the form of heat. After certain interval of time, if you want to get it back, you cannot get it. So the term is irreversible. The energy that has gone through it, that has been dissipated by this, cannot be taken back, retrieved back. So this is irreversible. I told you this is dissipative. Okay, and famous Ohm's law. From there we know V is equal to R into I, where V is the voltage developed due to the current flowing in the resistor. So if the what is the symbolic, what is the notion for current, what is the polarity? If current is flowing from this direction to this, this will be plus, this will be minus. That is, current flows from plus to minus. Okay, so if you pass a current I through a resistor R, you will develop a voltage V across the resistor. Clear? Then very simple thing, I'll explain again. When one end of the resistor is attached to the starting of another resistor, this type of arrangement is called series arrangement. Series. What happens? We have current I. So voltage, if this is R1, this is R2, this is R3, voltage V1, voltage V2, voltage V3 develops across the resistors. We can say if the total voltage applied is V, so what will be from KCL? V will be equal to V1 plus V2 plus V3. That is, V is I R1 plus I R2 plus I R3. That is I, if you take common, this is R1 plus R2 plus R3. That is, you can say this is I into R equivalent. You can visualize it like this also, that we have, instead of 3 resistors, we have 1 resistor, that is R. This is very fundamental. These things you have seen in your schools only. Why I am discussing this? Because from here we'll start and go to capacitance, inductance, and then RLC circuits, time domain circuits, steady analysis circuit. So it's important that you try to understand the approach by which we solve problems, or by which we go into a problem for solution. So this is, when you connect resistance in series, what you get is actually R equivalent is summation of R I, where I is equal to 1 to n. If you have 1, 2, 3, 4, n, this is resistor in series. Okay. What if we have resistors in parallel? You know it very well. If you have resistors in parallel, let's say 3 resistors, and here is your current source I. This is R1, this is R2, this is R3. So let's say this is current I1, this is current I2, this is current I3. What happens? From KCL, Kirchhoff's current law, at this node, this is one node. So at this node, I is entering and these three are exiting. So I equal to I1 plus I2 plus I3. Okay, I can be V by R, let's say the R equivalent, and from here what you get? V by R1 plus V by R2 plus V by R3. From here what you get? Your R equivalent, 1 by R equivalent is basically 1 by R1 plus 1 by R2 plus 1 by R3. So if you generalized it, it is I equal to 1 to n 1 by Ri. Okay. So this is resistors in parallel. The same approach we will be using for capacitors and inductors. First of all, let's see how capacitors and inductors behave when current passes through it. One more thing, power. Power is equal to V into I, voltage into I, or we have seen V is equal to IR, so this is I square R, or you can write V square by R. Why I am using small v and I? See, in electrical engineering, when you use capital letters, you mean the average values or the DC value, and when you use small letters, you mean the instantaneous value, the AC, alternating currents, the instantaneous value. So power is V into I, small one. Clear? So for resistor, the power dissipation is equal to this, I square R, or this. Now let's talk of the second element, that is the capacitance. Capacitance you have seen in your school. This is a parallel plate capacitor. What you do? There are electrical fields. Now when you charge a capacitor, that is you put a voltage across this capacitor, what happens? Electrical field, the energy is stored in the capacitor in form of electrical fields. Okay. Now this is not our subject. We are not going into the details of manufacturing of capacitor. Let's understand it as an idealized circuit element. So the symbol is this. This is a capacitor, or many times you will find this is how we represent a capacitor, because there also in practical capacitors the input terminals are actually marked. So this is the input and this is the output side of the capacitor in a two-port terminal, or simply in the start you can use this symbol. So let's say this is C, the capacitance is C. We pass a current I through this. So what this will be? I is given by C dV by dt. These all are time dependents. C dV by dt, that is a voltage V appears across this capacitor. Clear? I is C dV by dt. From here only you can see that dV is equal to 1 by C I dt. See. So when you integrate it, this is from 0 to V, that is you get from 0 to V. What happens when you pass the current, voltage starts to charge up. It's not instantaneous, that is the moment you apply current, this voltage won't appear across the capacitor. In case of resistor, the moment you pass current, voltage will appear, but here this will take time. You can see this equation, 0 to t. In certain amount of time, the voltage will start rising and reach a value. Okay, so 0 to V, 1 by C, 0 to t I dt, or you can write it as V is equal to 1 by C 0 to t I dt plus initial condition. We know when we integrate, we put k, a constant, so this is the constant, that is called initial condition. That is, if you had certain voltage when you started this current. So if that is the case, then that will appear here. If the initial condition is 0, that is when you put this current, this was 0, this will be equated 0. So this is capacitor. Okay, this is the current for a capacitor, this is voltage for a capacitor. Now we'll see what is power. I am rubbing this. Power, you know, is equal to V into I. So what we can do? V into I. See. Okay. And one thing I forgot. C is given as Q by V. That is, the V is the voltage developed across the capacitor, and Q is the charge. If C is capacitance of the capacitor, Q is the charge that actually accumulates on the capacitor, whatever type of capacitor it is. So power that actually flows into the capacitor is V into I. Now I is this, see, C dV by dt. So we can write it as C into V into dV by dt. So the instantaneous value of power, small p, is C V dV by dt. If you integrate it from 0 to p, what power it will do? See, here 0 to V, and we'll take dt here, that is see 0 to p, that is in 0 to time equal to t, what power has been transferred into the capacitor. That is what? That is work done. That is energy stored in the transfer of power. You know, power into time, this is actually energy. So power transferred into this capacitor, that is P into dt from here to here. This is actually your W, that is energy transfer. And this is what? C, and this is V dV. See, V dV from 0 to V. So what this will be? This will be V square by 2 from 0 to V. So what do we get? We get half CV square. This is the energy stored in the capacitor. So try to understand. We transferred power into the capacitor by passing current through it. So when current entered the capacitor, the voltage started rising up to the point where it saturates. So 0 to t is the time in which voltage becomes from 0 to, the voltage goes from 0 to V. And in this time, we transfer energy to the capacitor. And what is that energy transfer to the capacitor? That will be 0 to P dt, this equation. So that energy is this. So when you take a capacitor, apply voltage across it, leave it for some time, whatever be the time constant, and when you remove power source from this, I am not showing it here. See, we have a capacitor. What I am doing, this is a switch, and this is voltage. Okay, this is voltage source, this is C. I am closing the switch. So what happens? Current starts to flow from 0 to t. What happens? V goes from 0 to V, and in this time, energy in the capacitor rises from 0 to this W. Okay. Now what you do? You remove this switch. You make it open circuit again. That is, you have removed this source. The capacitor will hold this energy, half CV square. Now when you will connect a resistor through it, this energy will be dissipated in the resistor. That is to say, a current will start flowing into this circuit until this energy is exhausted. Okay. So if you have observed, you have capacitors in the fan. If you switch on the fan, and then what happens? The capacitor gets charged. This capacitor, it gets charged, and this energy is actually entered into the motor system to give it a ignition to move. Why? Because of inertia. In the starting, the fan is at rest. It requires certain energy to start rotation. So this energy is utilized there. Okay. So this is about capacitor. Now we'll see inductor. Now let's see inductance. And one thing I forgot to tell that time. the unit of resistance is ohms, the unit of capacitance is farads, and the unit of inductance is Henry. Okay, this you should keep in mind. Now let's see inductance. Similar to what we did for capacitor, we'll analyze it in the same way. This is an inductance or inductor. A device that is used for inductance is inductor. So this is spiral. This is inductance. Okay. Now if you pass a current I through it, what you will get is V, the voltage that develops across this, is equal to L di by dt. Now this device is also not dissipative in the sense we use for a resistor. It dissipates energy, but it stores energy also. The way a capacitor stores energy in the form of electric fields, an inductor stores energy in the form of magnetic field. These things you have studied in your school days, how it stores energy. We'll not get into that. Our topic is different. We will be dealing with inductors, capacitors and resistors as circuit elements. So V is L di by dt. From here, in the same way, what we get di is equal to 1 by L C V dt. Okay, 1 by L V dt. So the current will rise from 0 to I, and this will rise from 0 to T. So what effectively you get? The current in inductor is, if you make analogy with capacitor, there when you pass a current, the voltage rises from 0 to V. Here current rises from 0 to I. That is, you can write it like this: 0 to T V dt, and plus you will have a initial value condition. That is, when you put this current or when you applied this voltage across the inductor, if there were initial current, due to initial magnetic field stored in the inductance, that will be reflected here. Okay, and similar to what we did there, the power that enters into this system, which is stored as magnetic field, will be given by V into I. We have seen V is equal to, and V is what? L di by dt. So this is L di by dt. Similar to what we did in the case of capacitor, this will be P dt. So P from 0 to T, when you get the final P, what you get here is L and I square by 2. If you integrate it from 0 to I, 0 to I, finally what you get is half Li square, and this is energy. 0 to T, when you integrated it, you got energy. So energy is in joules. There also for capacitor, the energy will be in joules. So this is energy that is stored in the inductor. Similar to this, if we apply V, this gets charged in time t, then you remove it, this energy will be stored in the inductor. Okay, clear? So we have seen the three circuit elements R, C and L. Now a brief recap of KCL and KVL, so that when I start analyzing circuits, you don't get confused in it. First is Kirchhoff's current law. What it is? Let's say we have a current source I, and we have certain elements. Why I am using this? Because it may be a resistor or an inductor or a capacitor. So let's say this is Z1, Z2 and this is Zn. So what we do in Kirchhoff's current law, we take it as one node, and the basic idea is that all the current entering the node is taken positive and exiting the node is taken as negative, and the net sum of current I equal to 1 to n is equal to 0. This is Kirchhoff's current law. So if this is I, this is I1, this is I2, this is In, what we effectively get is that I minus I1 minus I2 minus I3 and so on minus In is equal to 0. Why minus? I is entering, so positive, and these are exiting, so this. So what it means is I is equal to I1 plus I2 plus I3. Okay, this is Kirchhoff's current law. And similar to this, we have Kirchhoff's voltage law. This is also called nodal analysis because we used a node. And for Kirchhoff's voltage law, we say mesh analysis. Why? Let's say these are two circuits. I am making two circuits. Let's say this is R1, this is R2, let's say this is R3, and this is another voltage source. Let's say this is V2, this is V1. Okay, how we perform KVL? If we talk of KCL, we'll see if this is current. Let's say a current I1 is flowing in this circuit and a current I2 is flowing in this circuit. Okay, so effectively what current is flowing in this circuit? If we take this direction, we'll have I1 in this direction, I2 in this direction. So the net current in this direction is I1 minus I2. When we are using in positive direction is this. So let's say this is minus to plus. So we'll have first V1, then I1 into R1. We know current enters, so this will be plus minus. So I1 into R1. Then we have, if we are considering current entering through this, then I1 is the direction. So this will be I1 minus I2 into R2. This will be our equal to 0. This is our first equation from Kirchhoff's voltage law. And second, now we are considering this direction, I2. So this will be positive and this will be negative. If we take this, this will be I2 minus I1 into R2 plus I2 into R3 plus 2 minus V2 equal to 0. This loop. So this is our second equation. From 1 and 2 we can have the different values. Okay. So this is called Kirchhoff's voltage law. These are meshes, so it is also called mesh analysis. So these were the basics. Now we'll get into RLC circuits.